Okay, so basically, before we end our lecture last Monday, we have looked into magnetic properties. We have understand what does it mean by magnetization, magnetic induction, magnetic field, and different types of magnetism. For examples, dimagnetics, paramagnetics, ferromagnetics, ferrimagnetics, and antiferromagnetics. And we also have looked into hysteresis causivity, is where when you actually apply a potential, apply a magnetic field into a material, so the domain or the moment of the magnet is start to be aligned. And if it has a permanent change, what happens is that it will, of course, give an effect of hysteresis. Causivity is almost the same like um, mechanical properties. When you apply a force, and then what happens is that the materials will experience permanent damage, and not really permanent damage, but permanent effect. That in the end of the day, when you stop the applied potential or the applied magnetic field, it's not going to return back into its original state, but rather than have something like offset into it. All right. So the last part that we are going to talk about in magnetic properties is on superconductivity. So superconductivity is very much an important properties. Basically, in various applications, for example, magnetic levitation or maglev train, we are using superconductors, also superconductivity for energy storage, for medical imaging and whatsoever. So probably before we, I think, define superconductivity, let's look at one video regarding on magnetic levitation train. I think this one is actually from University de Sherbrooke in Quebec, Canada. I think they have prepared a wonderful videos for us to understand. Okay, so you can see that this is actually a miniature where you have a superconductors. Okay, this type 2 superconductors, and it has been reduced into its critical temperature. So what happened is that when the material being reduced with the critical temperature, it start to give levitation effect. And when you have a rail that is made from different poles, north, south, alternatingly, and by a simple push, you can see that the material can move, and the movement is like frictionless, and and it actually give a very high speed. So this, imagine that you have a train and you put like superconductors and you reduce the temperature by adding liquid nitrogen. So what happened is that with a simple push into the alternating magnetic poles line, then the train can start to move, I think, with a high velocity. Right. So all this technology have been used currently in various application. I guess maybe you've seen speed trains in Japan, speed trains in China, in the Europe, Taiwan, and whatsoever. They are actually using magnetic levitation technology. And with this technology, we can ensure that the speed or the velocity of the train could be achieved at a high limit. So you can control also the velocity, and I think with this you can achieve as high speed as you want. All right, so that's all, I guess, for the video. I'm going to share slides for today. You guys find it interesting. I'm sure you will find it interesting when we talk about magnetic levitation. It's always, I guess, maybe looking into the future of train transportation. Okay, so things that you have seen just now is basically a material called superconductors. Okay, so superconductivity is actually the disappearance of electrical resistance below a certain temperature. So what happened is that you might see in the video that the researcher are, putting liquid nitrogen. So the function of liquid nitrogen is actually to reduce the temperature of the superconductors so that it can actually achieve a so-called critical temperature. So critical temperature is actually the temperature below which superconductivity is attained. Okay, and what happened is that when you reduce the temperature, okay, the electrical resistance will be disappear. So it means that you don't have any frictions or any sort of resistance created in a normal normal case. So superconducting behavior is represented in the graphical form as below. So you can see that as you increase the temperature for a normal metal, the electrical resistivity will be increased exponentially. But for superconductors, what happens is that when you actually increase the temperature and up into a limit of, a critical temperature, there's no effect of resistivity. So it's going to be like flat or the same, in the end. Superconductivity and magnetism. Okay. The first one that we can relate is the Meissner's effect. A material in its superconducting state will expel all of an applied magnetic field. So this is called Meissner effect. A magnet placed over a superconductor will actually give a flotation phenomenon that is known as magnetic levitation. So you can see from here in figure A, where if the temperature is actually higher than the critical temperature, you'll see that it will be a normal conducting state, magnetic flux will be penetrate. And when you put like a superconductors and underneath the superconductors a magnet, you will see that it will actually have a interaction, it will have an attraction. But what happens is that when you actually pour or maybe decrease the temperature of the superconductors by actually pouring the liquid nitrogen, for example, then it will actually giving an effect that the critical temperature is now larger than the normal temperature. Then when you put the magnets underneath it, the superconductor will start to float. It will actually expel the magnetic field. Okay. Right. So that is why you can see that in the footage just now, when you have levitate materials, okay, this one is actually achieved at the critical temperature, okay, and you have a magnet, okay, and imagine that if you have magnets that have a different poles, north, south, north, south, then because of this one will levitate, okay, with a simple push, it will actually move, okay, around it. If you put like a similar pole at the side, so what happened is that there's no movement at all because like it's going to float only. It's not going to like mobilize. So it needs a opposite pole so that it will give like a repulsion at the same time, floating repulsion, floating repulsion, and then with a push, then you can see that it will actually move while floating. Okay, so some might wonder, like, if we use this kind of technology for train, how we are going to stop the train if it is actually levitate and it's been pushed with, with a simple force. So anyone knows how actually we are going to, stop the train if we use this kind of technology? Can I ask Atira Adnan? Atira ada tak? Atira. Senyap. Okay. Balkis Hanani. Balkis.
Yes, doctor.
Okay, so Balkis, what do you think? If we use this kind of technology for maglev train, how we are going to like stop the train? Because now it's floating, I think above the critical temperature, and when it moves, so how actually you reduce the speed and how you actually make sure that I think the train doesn't like levitate anymore.
Maybe reduce the temperature.
Reduce.
Temperature.
So actually we reduce to achieve critical temperature.
Oh, okay. Increase
Okay, right.
opposite one.
Okay. So betul lah macam I think what you said. Actually, in order to reduce the Meissner effect, we have to increase back the temperature. So when you increase back the temperature, so the levitation effect will start to reduce, and finally it will be attracted to the magnet. So this is how the material reduce the speed, and they does their braking system. So dia tak pakai brake because it's like levitate in. It doesn't have like, maybe it will have a like I think a wheel, for example. But I think most of the maglev train, it doesn't have a wheel. Dia tak ada roda. So I think in order to brake or to slow down the speed, they just increase the temperature slightly so that it will have an interaction with the magnets, and finally it will stop. Okay, all right. So moving on to the next one, we are actually looking at the different types of superconductors. So you do have different types of superconductors. For example, over here, I give, I think, examples of type 1 and type 2 superconductors. So type 1 superconductor actually means that if the field is increased, some of the superconducting materials come back to a normal conducting state above the critical magnetic field. Okay? And for type 2, in another class of materials, the field begin to intrude above a critical value of a applied field at the higher field. Okay, it turns into a normal conductors, and the transition is gradually unlike in type 1. So this is actually called superconductors type 2. Okay, so what's the difference between it? So the difference between it is that the type 1 superconductors, if you actually reduce the critical temperature, okay, so some may come back into a normal conducting state, but some may not. Okay, so for example, like lead and aluminium. So if you actually apply the critical temperature, I think it still have the conducting properties, but I think not necessarily. Okay, in case of type 2 superconductors, okay, if you actually reduce the temperature, so what happens is that at the higher field, it will return back into a normal conductors. But I think if it is at the lower field, then it doesn't actually return into a normal conductors. So that is why I think it depends on the types of application that you are going to use for your superconductors. Then you will use different types of superconductors, right? So the application of superconductors can be seen, as I said, it is used in maglev train, where this train will be levitate, and it can actually move at the high velocity. And apart from that, there's also different types of device that use superconductors. For example, MRI, maybe you've heard of MRI, magnetic resonance imaging scan, is actually being used to scan your internal organs, and it can give a diagnosis to doctor what kinds of disease that you have. And there's also another application with regards to energy storage or electrical generators, high efficient electric generators, and also energy storage. And apart from that, superconductor is also used for squid. So don't I think, be confused with Squid Games. I'm sure that you are watching Squid Games, but Squid is actually refers to superconducting quantum interference device. Okay, so this is actually an quantum interference device, and it's normally used in electrical, I think, high-end electrical or AI technology. And finally, superconductors is also used in collider, large hadron collider. So I think the terms collider is something alien to you guys, but I think in some countries they are actually, I think, studying the effect of collider, because a collider can produce a massive amount of energy. So those who didn't understand what does it mean by collider, so collider, it means that you have a tube, where it will be in vacuum, and at the same time you will actually I think bombard the particles or atoms, that it will move with a higher velocity, and when it collides, okay, it will actually produce a very huge amount of energy. Okay, so in this case, superconductors is being used because of you want to have it at high velocity. So the higher velocity it is, I think the huge energy that it will produce. Okay, right. So that's wrap up the I think magnetic properties. We have already looked into what does it mean by magnetic induction, different types of magnetism, or ferromagnetics, paramagnetics, and dimagnetics. Hard magnets and soft magnets. So hard magnet, it has a large coercivity because having a large permanent effect, and soft magnets, the magnetization effect is normally temporary. Then you will have a small coercivity. And we also have looked into different types of application for magnets, for example, superconductors, maglev, and others. Okay, so that's actually the end of I think chapter 10 B on sorry 10C on magnetic properties. Okay, is there any questions so far before we move on to the next chapter, thermal properties? Okay, going to share. So those who have not downloaded the lecture notes, I believe I have uploaded it in the e-learning. So please have a look. Right. So moving on to the next chapter, it is actually on thermal properties. And when we talk about thermal properties, it is also have some relation with electrical properties and also mechanical properties. Okay. Imagine that if you have materials, either metals, either polymer, either ceramics, if you actually expose this material into heat, then different kinds of properties that it will produce. It depends on the interaction, vibration, and anything that the material has. But I think in a nutshell, you will see that all these material produce a different thermal behavior. Okay, so in this chapter, actually, we are going to see how do material respond to the application of heat. Okay, and apart from that, how do we define and measure heat capacity, thermal expansion, thermal conductivity, thermal shock resistance, and how do the thermal properties of ceramic, metals, and polymers will differ? Okay, right. So before we go into the basic definition, probably we need to understand what sort of or what modes of heat transfer that you can actually observe. Imagine that you have a pot, as a metal pot. Okay, you are doing some camping lah, okay, and you put on fire. Okay, and inside this pot you put like water. You want to boil water. Okay, so when you hold the pot, okay, so what happened is that you will feel the heat after a certain time. Okay, initially maybe you didn't feel it, but after a few minutes you will start to feel hot, okay, on your palm. So what happened? So what is actually happening is that the heat from the source, which is from the fire, it's been transferred into the pot and finally goes into the surface of your hand. So this mode of heat transfer is known as conduction. So conduction is actually the transfer of heat or electrical current from one substance to another by direct contact. Okay, and while holding the pot, you will start to feel your body start to feel hot as well. It is not because of from the effect of holding the pot. Could be partly, but I think the other actually coming from the radiation. Okay, the heat coming from the fire itself. So this is actually called radiation. So radiation is the energy that is radiated or transmitted in the form of rays or wave or particles. Okay. And finally, if you observe into the pot, you will see that the water, which initially have a initial temperature at room temperature or slightly below than room temperature, and when you put it on fire, you start to see that the water start to boil, start to vaporize and whatsoever. So the modes of heat transfer that happens over here is known as convection. So where convection is the transfer of heat through a fluid of, I mean, either liquid or gas caused by molecular motion. So water will actually absorb the energy obtained from, I think, external source like fire or whatsoever. And after that, the water particle will start to vibrate. And when it vibrates too much, and it will actually become hot. And when it become hot, then it will, boil and whatsoever. Okay, right. So heat capacity. So this is also not something alien to you guys. You've heard about heat capacity during high school, during your matriculation, during your STPM, A levels, KFT in KFT as well. Okay. So heat capacity, maybe in your mind, you start to think about CP, yeah, but you have to understand that heat capacity also have like other terms like CV with regards to constant volumes and whatsoever. So heat capacity is actually the ability of material to absorb heat. Quantitatively, the energy required to produce a unit rise in temperature for 1 mole of a material. Okay. Therefore, if you want to calculate heat capacity, it is always the difference of energy input Q over delta T. Change of temperature. There's two ways to measure heat capacity, okay, which is first, it's known as CP, okay, heat capacity at constant pressure. This is the common, I think, phenomenon that you see a lot. And then you have a CV, heat capacity at the constant volume. Okay, this indicates that you are studying different pressure effects and whatsoever. So usually CP is larger than CV. And the unit of heat capacity is always related with energy, because energy is actually in joule. So you have to use, like joule over mole over Kelvin unit for heat capacity. All right, so the dependence of heat capacity on temperature. So heat capacity will increase with temperature. Okay, so as you increase the temperature, your CP or CV will increase as well. For solid, it will reach a limiting value of 3R. R is actually a gas constant. 3 times of gas constant value, then your heat capacity will be flat, or it will be constant in this case, right? So from atomic perspective, energy is actually stored as atomic vibration, and as the temperature increases, the average energy of atomic vibration will start to increase as well. Okay, so we talk about atomic vibrations and everything when I think a material has been heat up. So atomic vibration are in the forms of lattice wave, or so-called phonons. So I think when you have a material that is not being heat up, the lattice position is actually fixed. But when you heat it up, then what happens is the material start to like become disturbed and start to vibrate, and it is not actually at the normal position. It has been displaced because of like vibration. So this is actually what we call phonons or atomic vibration. Right. So for specific heat, the comparison between different materials, it is always important to see that or to notice that different materials will give a different heat capacity values. Of course, when we compare between polymers, ceramics, and metals, polymers will have higher heat specific as compared to ceramics and also metals. So why does these things happen? Anyone have a definite answer for this? Uh, Han, I saw the name Han. Han only. Siapa Han? Han, are you there? No, Han is not there. Okay. Mardiana Zubir. Mardiana ada there? Mardiana.
Ada doktor.
Okay, so Mardiana, what do you think? Why each materials as listed over here, polymer, ceramics, and metal have a different heat capacity? How did you? I mean, how do you explain this?
Macam mana nak explain eh?
Hmm.
Maybe because the type of bond between the material itself.
Ah, very good. That is actually the answer. Okay. So, if you actually compare between polymers, ceramic, and metals, so you know that each materials have its own definite bonding. For example, like metals, the interaction is mostly metallic bonding. It's very strong, very rigid. Okay, and if you actually heat the material, maybe the vibration will be slightly less as compared to ceramics and also polymers. Okay. Meanwhile, for ceramic, we know that the interaction is mostly like ionic bonding. Okay. And then for polymer, it's mostly like covalent or secondary bonding. So covalent bonding is, I think, is the least, strong bonding. Then what happens is that when it actually receive energy from external, so what happens is that it tends to vibrate even greater than I think those in ceramic and those in metals. So that is why you will have a different heat capacity values, right? So over here, I think you see that polymers will have a higher CP value, ceramic slightly moderate, and metals will have the least CP value. So why CP significantly larger for polymers? Okay, it is larger because it has higher linear coefficient or alpha, and we are going to see alpha after this of thermal expansion for polymer. But what relates linear coefficient with a material or with heat capacity is actually the types of bonding. Okay. Um, okay. Whatever amount of heat they absorb from the surrounding or any source, most of them is used in increasing interatomic distance. When it vibrates, it will actually create or maybe produce like a distance, interatomic distance, rather than increasing the temperature of the polymer. So polymer are covalently bonded materials and metals are metallically bonded materials. Okay. Right. So next up, we moving on to thermal expansion. So have you ever noticed that there's also one experiment during high school or even in primary school that when you put like a rod eh, on the candle or on the lid, what happens is that the length of the rod will start to become slightly increased. Okay, so what caused these things, or why you see that during daytime, the cables, okay, the electrical cables will start to become like, stress, or it will become like slightly maybe stiff as compared to during nighttime. So all these are actually with regards to so-called thermal expansion. So thermal expansion actually defines as the material change in size when temperature is actually changed. So you have an initial temperature which is slightly lower, and then after that, when you actually increase the temperature, what happens is that the material have a tendency to elongate. But the elongation is not really tremendous. It's not really large, like from 1 centimeter. When you put fire, it become like 1 meters or something like that. No, it would be slight. Displacement maybe from 1 centimeter. When you, heat it up, it become 1.01, for example. You have some small displacement there. Okay, so all these actually explain that it has like interatomic vibration or distance, which cause later on thermal expansion, right? So thermal expansion can be related with I think linear coefficient and also change of temperature. So that is why in this case you have a formula that delta L is actually the length. The change of length is actually length final minus length initial over length initial. That is equal to alpha. Alpha is actually linear coefficient. It is a fixed volume, a constant value, value for each materials. And finally, delta T is the change of temperature. Temperature final minus temperature initial. A comparison between different materials. For thermal expansion perspective, you have a so-called asymmetric curve and also symmetric curve. Each and every materials, when you heat it up, it can actually give thermal expansion, but some also didn't give any thermal expansion. Right. For asymmetric curve, you will see that as you increase the temperature, it will increase the interatomic separation. Thus, it will actually result thermal expansion. For this case, maybe we just give an example of metals, for example. So you put metal. So what happened is that when it start to vibrate, okay, it has an interatomic separation. It will actually experience thermal expansion. But let's say that you have types of mineral or maybe ceramics that you heat it up. So what happens is that there's an increase in temperature, but there is no interatomic separation, which finally results no thermal expansion. So if you heat up ceramics, so you didn't see that the ceramics start to elongate or what. It just remain as that. So that is why I think ceramics or minerals normally being used as a thermal insulator, because it can actually absorb heat, but it didn't cause any changes to the structure of the material itself. Okay, so for this kind of things, we call it as symmetrical curve for thermal expansion. Right. So a comparison between thermal expansion between different materials. Okay. These again with a relation of linear coefficient. Okay. So polymers still have a high thermal expansion because it has a higher linear coefficient as compared to metals and also ceramics. Okay. So ceramics, as I said, will have the least thermal expansion as compared to metal. Metal will have a thermal expansion. So why does alpha generally decrease with increasing increasing bond energy? So this actually because of like materials that have a larger alpha value will have a weaker types of bonding, and with that it will actually cause an increase in thermal expansion. Okay. All right. So let's look at the examples. Okay. I'm sorry you might see all these writings on this. Writing is actually I made it yesterday during the pre-recording. Okay. Right. For example, you have one copper wire 15-meter long that is cooled from 40 to -9. How much the change in length it will experience? Okay. So over here, we know that you have a wire, copper wire, with an initial length of 15 meters. Okay. And then there's two temperature values given. The first one is actually at 40 and -9. Okay. So what do you think? Which one will be, initial temperature and final temperature? Of course, we know that initial temperature because it's mentioned over here. It is cool. Okay. So the initial temperature is actually 40 and the final temperature is actually -9. But if you actually understand thermal expansion means that from a colder temperature, it's been heat up and it will elongate. So in this case, if we want to put this into a thermal expansion phenomenon, you should actually put -9 as your initial temperature, and your final temperature will be 40, because As I said, thermal expansion, you will heat and there's an increase of temperature. But the question is actually asking the material has been cooled. So it's actually in reverse. So you have to actually reverse the state of temperature as well. So how much the change in length? So what you are going to find is actually delta L, delta L value, the change of length. So taking into the formula of thermal expansion, delta L over L is equals to alpha multiplied with delta T. Okay, so delta L you can get it by multiplying alpha multiplied with delta T multiplied with L. So alpha is 16.5 multiplied with 10 power of minus 6, and then after that multiply with the change of temperature 40 minus with minus 9, then multiply with the length which is 15, and in the end you will get values which is actually equals to 0.012 meters changes. Quite simple. We look into another examples. You have a circular hole with a diameter of 2 centimeters made in an aluminum plate of 0 degree. What will be the diameter at 100 degree? So given that alpha value for aluminium is 2.3 times 10 power of minus 3. Okay. So here also we use the same formula. It's just that the case is given in the diameters, but we still can assume that diameter is equals to the length because I mean it's like a cylindrical hole. It's not like three-dimensional shape. So we are going to measure or to know what will be the final length. So the initial length is 2 centimeters. Initial temperature is 0, final temperature is 100, then alpha is equals to 2.3. So you can actually put it into the formula, and I think in the end you will get the final length is equals to 2.46 centimeters. Okay, so this is also quite straightforward examples. Okay, so we are moving on to the next one, which is on thermal conductivity. So thermal conductivity is the ability of the material to conduct, I mean to have a conductivity. And the conductivity is by means of thermal. So the ability of material to transport heat is actually known as thermal conductivity. So here we are considering Fourier's law. Q is equals to minus K multiplied with change of temperature over change of X. Change of X is actually the change of distance. Okay. And in the atomic perspective, atomic vibration and free electrons in hotter regions transport energy to a colder region. So this always that you see, I mean, if you have like a rod over here and you have a source, so I think after a certain time, you will see that your hand start to feel the heat. I mean, and this is actually caused by the thermal conductivity. And by, I mean, deriving Fourier's law, you can actually calculate thermal conductivity by using this formula. K is equals to QL, Q multiplied with L over A multiplied with delta T, where K is actually thermal conductivity in watts over meter Kelvin, and Q is actually the heat transfer, okay, through the material, normally in joule, okay, and A is actually area in meter square, delta T is actually the difference in temperature. So L, what is L? L is actually the distance. So example, calculate the thermal conductivity through a conductor when 30 kilowatts of heat flow through it, having a length of 4 meters and the area of 12 meters square if the temperature gradient is 40 Kelvin, sorry. So from here, you can actually use the formula K. So Q value is equals to 30 kilowatts. Length is 4 meters, 30 times 40. Okay. And then over area 12 multiply with 40. Okay. And you have to, I think, remember that the heat flow, I mean, the heat flow values given over there is in kilowatts. So you have to multiply with power of 3, should be. Okay. And finally, you will get the thermal conductivity value, which is actually equal to 250 watts over meter Kelvin. So question 2, what is the temperature gradient if the conductors at 70 Kelvin after a flow of heat of 20 kilowatts reach a temperature of 100 Kelvin? Okay, so here you just want to find what will be the temperature gradient. Okay, so in order to find the temperature gradient is very simple. You just like subtract the initial temperature with the final temperature. So 100 minus with 70, you will get 30 Kelvin. So thermal conductivity in comparison, of course, metals will have higher thermal conductivity values because of the atomic vibration and motion of free electrons, okay, as compared to others. Polymers will have the least thermal conductivity. Okay, so ceramic will have a moderate thermal conductivity values. So all these are actually depend on the ability of the material to absorb heat and then after that vibrates and after that give a motion. Okay. I think before we end, there's a few, points on thermal stress. So we have looked into, thermal expansion. We have looked into thermal expansion and thermal conductivity. So now it's on thermal stress. So thermal stress is actually a combination between thermal effect and also mechanical effect. It occurs due to uneven heating or cooling and mismatch in thermal expansion. So have you actually imagined that if you have a piece of a glass and then you pour hot water or boiling water inside it, and after that, when you put, when you remove the boiling water, the glass is still hot, and immediately you put in ice bath. So what happens is that you will see that it will give some crack, okay, or maybe it become break or whatsoever. So this actually cause a so-called thermal stress. Okay, so there's also a mismatch in thermal expansion. Then the stress effect can occur after that. So thermal stress can be calculated. Stress is still in sigma. So sigma is equals to E. E is actually modulus of elasticity multiplied with linear coefficient and multiply with the change of temperature, right? So examples, a brass rod is stress-free at room temperature. It is heat up but prevented from lengthening. At what temperature does the compressive stress reach 172 megapascal? So the original condition is that you see that the material have a initial temperature and also initial length. So assume that unconstrained thermal expansion, you'll see there's also some, displacement or some changes of length. And compression of a specimen after you, stop the temperature, you see that from the expansion, it start to compress, or you return back to the original length. So the thermal stress can be calculated directly from this formula. Okay, so arranging and solving T finals will give, the value, because I think over here they are asking what will be the final temperature. So you can actually put the initial temperature 20, sigma value minus 172 megapascal over epsilon. So over E. E is the modulus of elasticity for a brass, which is 100 gigapascal at this temperature. And linear coefficient for copper is equals to 20 times 10 power of minus 6. So always remember that whenever you have compression, the force or the type of stress that you values that you are going to put is always in negative value, because it is actually not like tensile. Tensile, you actually pull the materials. Okay, so it will going to be positive, but compression, it will actually shorten the distance and whatsoever. So that is why the stress value that you need to put in the formula, it must be in negative sign. Okay. And lastly, we have this so-called thermal shock resistant, thermal shock resistance occurs due to non-uniform heating and also cooling. It's also the same as thermal stress, but in this case, we assume that the top layer is rapidly cooled from temperature 1 into temperature 2. Then this will create a so-called quenching effect, where in the end of the day, there's, like shock resistance. It will create crack and it will damage the materials. So part of the examples that you can see is from the thermal protection system in, I think, Space Shuttle Orbiter. Okay. After the aerospace mission has been ended, so the astronaut will go back to the Earth and using a shuttle orbiter. Okay. So when it enters the atmospheric environment, gravity is applied. So you see that the amount of friction, amount of force being applied to this orbiter is quite huge. If it is not being protected, the body of the shuttle orbiter is not protected with a highly resistive material, what happens is that friction can cause heat, heat can cause fire, fire can cause explosion and whatsoever. Okay, so that is why in a space shuttle orbiter, it is equipped with a thermal protection system. Like for example, in the fuselage, fuselage is the region where the astronaut or the pilot they stay at this region, and at this point you have a more how to say more force or more frictions that occurs in this point. So it is actually equipped with reinforced carbon-carbon that normally the temperature is quite high, quite resistive, 1600. Okay, and at the side, at the wing and whatsoever, it is equipped with silica tile. So silica tile have a slightly moderate temperature, degrading temperature around 400 to 1200. So with that, I guess it can actually reduce the frictions, and when it absorbs the heat, it didn't cause any damage to the space orbiter. Otherwise, the temperature is very hot and it will cause fire and whatsoever. So I think that's one incident. Maybe you can check out on the YouTube. I don't know. I give you a link over here, but there's one incident happened in the US back in I think 80s or 70s. I think Challenger incident. You may actually check it on YouTube, where a piece of reinforced material is being displaced. Dia tercabut during uh, during the launching up of the rocket. Okay, masa roket tu nak pergi ke atas, a piece of thermal protection system on the body of the orbiter tu dia tertanggal, displaced, dia terkeluar, tercabut. Okay, so when the mission finish, I think the orbiter enters Earth. So what happened is that when it enters, because of just one piece of material have been displaced, so what happened is that in the end, when gravity force is applied, friction, because of satu piece yang hilang, one piece missing, it caused fire and the orbiter crash. I think it explodes first. It explode and crash. So this is a very catastrophic, incident. All astronaut was, declared dead, and I think later they found out that during the mission system, during the mission, when they launched the rocket, they noticed that there's one piece of the material have been dislocated. It been displaced, and they didn't realize that. Okay, they didn't fix it, and I think what happened is that when they go back into Earth, actually they just, the orbiter just burned, and I think crashing all the astronauts. Okay, so you can check this incident on YouTube. So it's a sad day for NASA and others. Okay, so as a summary for this, chapter, we have actually looked into the definition of heat capacity, coefficient, linear coefficient, thermal conductivity, and also thermal shock resistance. Okay, so I think most of these definition have been mentioned, but what is the importance for this chapter is you know how to calculate thermal expansion, thermal expansion effect, the length, different of length and different of temperature with different kinds of phenomena, situation given. You know how to calculate thermal conductivity, and I think maybe give some examples on thermal shock resistance materials. So this is actually the essence or the key for this topic. Okay. All right. So I guess that marks the end of our thermal properties chapter. I guess on Friday we are going to have optical properties, the last one on material properties before we start with the last chapter, chapter 11 on corrosion and degradation of materials. So I'll stay back if you guys have a question. Remember, today we are going to have quiz. So our quiz is basically on electrical properties and also magnetic properties. I will post it right away after this. And the date, the due will be 5 p.m. today. So hopefully you'll find some time to do it. I will stay back if you guys have any further question. But if you don't have any question, I would like to thank you all for listening the lecture today. And hopefully to see you on Friday. I will let you know the time, probably around 2:30. Okay, Friday. And with that, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Thank you all.